Good morning, all. I'm Dr. Anand, Associate Professor in the Department of Information Technology. Just a minute. Today topic is review on application of deep learning for cyber security. I would like to invite our speaker, Mr. Prasath. I privilege to introduce our speaker, Prasath. He is working as a software architecture in medicine solution. He has and 4 years of data science architect. He has designed, developed, and provide software solution, technical governance, support, and developer team, evaluate and recommended tools. It ensures qualities and security of technologies and process, collaborate with the peer organization, and troubleshoot the problems quickly and efficiently. It also he know that RPA solution and configure, manage, and CL and CD. He has experience in static modeling and predictive modeling using machine learning and deep learning. He has good knowledge in data analytics and cyber security and various technologies. He has good real-time experience in the field of emerging technologies. Okay, thank you, Prasad. I hand over the session to Mr. Prasad. Prasad, you can continue.
Yeah, thanks, Anand, for the brief introduction about me. And so, before we start, good morning, everyone, once again. So, today's topic is review on application of deep learning for cybersecurity. So, we are going to see about, two particular algorithms. It's kind of it's not just a review. One particular algorithm, we just deep dive and learn, learn few things about deep learning and how the data has been extracted from the system and how it has been analyzed and how it has been cleansed and how it has been, scaled out, everything. Okay, and finally we'll give some give that particular input to the deep learning model, and we will also see that what kind of a deep learning it is, what kind of algorithm it is, and I will just give a brief about it. And so finally, what is the output of the deep learning and conclusion on that. Okay, let me move to the next slide. So, in any field, okay, not only in cybersecurity, the machine learning field, the deep learning is becoming more advanced, okay, when compared to traditional machine learning algorithms. So there is nothing with the machine learning algorithm. It's, we cannot say that is poor. Okay, they have some ideology of processing the limited, size of records. Okay, let's say if we're going to process some 1 terabyte of records, okay, the machine learning algorithm, the traditional machine learning algorithm will not be suitable. So in that case, the deep learning have come in. So it has the capability of running very large data sets. So even you might have heard about that in the world of big data. So the deep learning, it will be very useful to analyze a large set of data. Okay, and one more thing is cybersecurity also is very important thing as of now. Okay, because it is becoming a compliance for every corporate to implement the cybersecurity policies. Okay, because a client that we are giving the projects to the particular corporate or software company, what they are expecting is they want their software or they want their data to be secured at any cost. Okay, so they want to make sure the data or the application that you that the corporate provides should be secure. So then the question raises, right? So how you make sure the data is secured? Okay, there comes some of the tools. Okay, and several tools, which is detecting the malwares and intrusion attacks, everything. But day by day, what happens is they have a set of rules, okay, and let's say they have some 100 set of rules, and let's say the threads are coming in different colors nowadays, okay. So suddenly you may not expect the new way of attack come into the industry, okay. At that time, the set of rules, 100 set of rules that is defined already may fail, okay. So in that case, we need some intelligence, okay, not the automation. So far I have explained this just automation of the cybersecurity tools, cybersecurity. Okay, whenever you have software for cybersecurity, it is a kind of automation. There is nothing with that. Okay, it has some set of rules. That's all. Okay, when we compare to the machine learning or deep learning, whatever it is, you can just take it as AIML, artificial intelligence and machine learning. It has some intelligence to learn the data and it identifies some pattern inside it. Also, it has the capability of learning new data coming in. I mean, new pattern. Okay, let's say if the system feels, I mean, if the deep learning algorithm or machine learning algorithm feels that this particular pattern is new to the environment, then it easily alarms the appropriate authority. Okay, that is how it comes. So there the importance of deep learning and machine learning rises. Okay, and we will see those algorithms. I mean, especially deep learning and deep learning for intrusion and detection and malware detection in upcoming slides. Okay, yeah. So as I told already, the threats are becoming. I mean, it's scaling by itself. Okay, the hackers or attackers, they are they are becoming intelligent, right? So they will always search that how to intrude. I mean, how to make an intrusion inside the network. Okay, how to send the malware software to the particular I mean, hardware device or any environment. Okay, any large environment where the clusters of servers will be there. Okay, so so that's how the cybersecurity becoming more important. Okay, and so as I told already, cybersecurity is a set of technologies and process designed to shield computers. Okay, so it has to protect the networks, programs, and not only, I mean, there are several ways of security, right? Information security, hardware security. Okay, so something like that. So it has to secure not only the data, it has to secure the software and also hardware environment. Okay, so yeah, we will see there are several ways to use this deep learning for the cyber security. Okay, we have taken two particular algorithms. We'll get the data, and there are several steps. You're definitely going to see those in upcoming slides. Okay, yeah. So in the third point, as I told already, so previously we have some automation. We have some software that does some automation. I mean, automation for detecting the malware or intrusion attacks. Okay. So now the deep learning comes in. So it has the capability to identify the identify the issues with intelligence. That is the main thing here. Okay. So previously we had the software that with the rule-based algorithm, they don't have the intelligence and they will not learn by themselves. Okay, so that's the deep learning here. Okay, now so there are two use cases. Okay, we are going to jump in the first use case in cyber security, the intrusion detection. Okay, so intrusion detection is nothing but, okay, there is something entered in the network. Okay, I mean, it might be a program. Okay, that checks the chance for the flow. Okay, and used to do unauthorized access to the user or do some unauthorized activity inside the network. Okay, so we have to detect this, okay, smartly, so that we can alarm or take an action accordingly whenever the intrusion attack is. Okay, now the image that you are seeing is seeing at the right hand side is the actual data set, and you can download the data set from the below link. You can see that link which is highlighted in blue color. Okay, so it varies. I mean, every OS will have their own structure of data, but nevertheless they will definitely give the relevant data. Okay, but the the way they structure the data will be different. Okay, so the data that you are seeing is one kind of a data, okay, which you can see that days, date, description, and size. You can uh, you can see that in the screenshot. I mean the image at the right hand side. So the beauty of deep learning and machine learning, it has no capability to understand the text or image. So the question raises, so the data that you are giving is in the format of text. I mean the third column description is purely text. Okay, and everyone might have heard that there is some technology called natural language processing. So that has some intelligence. I mean that is a AI technology. So which will identify, which will understand the context of the sentence, and it will reply to the user. So say for an example, if you take any web, let's say if you are going to buy Azure, I mean if you are going to subscribe Azure DevOps in cloud, okay, so you like to contact the Microsoft team, but nowadays the chatbot has becoming global. Okay, what they are doing is they have the chatbot that helps you immediately. Okay, I mean on your queries. Okay, whenever not only Microsoft, wherever you see, you can see chatbots for every website or product. Okay, most probably nowadays. So what that does is, okay, as I told already, AI is fully I mean any technology under the AI, deep learning or machine learning or whatever it is, they will understand only the numerics. Okay, not the text. Okay, not the images. So so NLP is the best example I can take at this time. So if the chatbot receives a text from you, it will convert them into a number. Okay, set of numerical values. Okay, and then it gets those numbers to the I mean prediction. Okay, then it will reply once it has understood the sentence. Okay, in the way of numerical format, it will reply to you. So that way, okay, the natural language processing, I mean the AI technology deals with different format of data. So finally, I cannot say it deals with different format of data. We have to feed the deep learning model or machine learning model within with numbers. I mean every columns. I mean in deep learning, I mean the world of AI, artificial intelligence, we used to call that as features, not the columns. Okay, so every feature should be in the numbers, numerical values. Okay, so then you can understand now that description column is going to be converted as a numbers. Okay, but in this intrusion detection algorithm, it will be something different. Okay? I will show that to you. Okay, before we jump in actual deep learning algorithm, so we can see that. So exploratory data analysis is there. Okay, one way of reading the data and analyzing the data. So I will just give a quick brief about it. Whenever you receive a data, you do a data cleansing first of all. Okay, so data cleansing in the sense it has to be clean in such a way it should not have a duplicate, it should not have a null values, it should not have a irrelevant values. Okay, if you feel that the irrelevant value is there, then you will remove those. Okay, and one more thing is after cleansing, we will do exploratory data analysis. What it does, okay? So we have univariate analysis, we have bivariate analysis, we have multivariate analysis. What we do is univariate analysis,
Prasath,
nothing but yes, Anand.
Your voice not audible, I think. Can you check?
Hello, is it fine now? Is it fine now?
Can you speak?
Is it fine now, Anand?
Yeah.
Okay.
Now it's okay.
Okay, that's fine. So I think my headset's making some problem. Okay. Okay. So yeah, so as I told, the exploratory data analysis, which is very important thing before we do machine learning algorithms. Okay. So what we do is there are several ways of univariate, I mean, exploratory data analysis. One is univariate analysis. It's nothing but you have to pick one particular column and check how the data is scattered across. Okay, so we do check that some mathematical way of identifying the data is normalized or not. Okay, and then we will check that the data is in balanced. Okay, so let's say if we have values male and female, the data set, let's say you have only two values for the male and we have some 100 values for female, then that data set will not be useful for the prediction. It has no capability to predict something. Okay, so then in that case we will do several things. Okay, I mean there are several steps to populate the data. First of all, we can just directly request the user, I mean the business, to provide the relevant data, okay, and the balanced data set. So if that is not the case, if you feel that only 10 to 20 columns are missing or limited number of columns are missing, then there is a methodology called sampling. We will do some samples and attach that to the original data set, okay, and get them for the prediction. We also check that some business, okay, some business does not want the prediction and all. They just want the insights only. So in that case, what we do is we use Python library, and there are several libraries, and used to plot them on Jupyter Notebook IDE. So to identify how the data has been scattered. Okay, so let's say in a banking sector, okay, let's say the personal loan. If you take a personal loan as an example, if you get the data of personal loan information, okay, you can see that the person with the age of 35 or less than, I mean, from the age of 30 to 35 might have opted the personal loan. But whereas in person above in the age 45 would not be. Okay, so you can just plot them in the Jupyter Notebook and get them as a image, and you can submit to the user, so that they get some intuition that the age 45 aged people, how to attract them, okay, how to offer them with a better loan tariff. Okay, so they will look at some way. There are a lot of analysis. There are a lot of insights will be identified using the exploratory data analysis. So one that you are seeing is part of the exploratory data analysis. You can see that data set that we have is normal and anomaly. Anomaly is something issue. Okay, so normal, you can see that normal data is very high, anomaly is very less. So in this case, I cannot promise that the machine learning will do a better accuracy while detecting the anomaly. Okay, so let's see. Okay, there are several ways of plotting diagrams. Okay, so one that you are seeing is kind of a kind of a plot which is available in the Python library. Okay, and yeah, data pre-processing, as I told already. Okay, so we have to receive the data. You know, that is separate. We have to engineer do some engineering on the data for sure. So sometimes you will have the actual structured data. So you may end up with modeling, data modeling. Data modeling is nothing but you will have large data in an environment. Okay, what it does is there are several tables, maybe 100 or 200, but all the tables will not be recorded for your machine learning. So, and one more thing I like to highlight here is, so if you have the data set for with 10 to 15 columns, okay, that can be acceptable for the machine learning. So think that if you have more number of features, let's say 100 or 200, so then the machine learning will not give a better model, okay, because whenever you increase the features, the model try to overfit the algorithm. Okay, in that case, these pre-processing step will jump in and reduce the features. I mean, features means the columns. Okay, so that is appropriate for the algorithm. Okay, so for this we do normalization. We check the data is normalized or not. We also check and the data is correlating with the output. Okay, let's say we are going to detect normal and anomaly detection. Okay, okay. You have, I mean, the features that you are using as a data set should match that with of anomaly. I mean, the target value. Okay, so right now what you're seeing is the classification algorithm. If you go and check some regression algorithm, let's say you can take an example of how I mean, what is the quantity of milk that a cow can yield, okay, for a day. Okay, so the input parameters will be the quantity of food, okay, supplied to the cow. Okay, in that case you can see the relationship between whenever food quantity increases, the quantity of milk yielded by the cow increases. Okay, so that's how it comes. So in this case I cannot highlight that particular methodology here, as it's a classification algorithm. Okay, because it will be a relationship between them, but you cannot see, there will be a how can I say, there will be dispersion between the two features. Okay, uh, which is another, it is called a relationship actually. In regression it will be easy for you to understand. It's not, it's not something like only for a regression problem you can find the relationship between the target variable and the independent variable, but you can also do the same thing for the classification algorithm also. Okay, but what I'm saying is they will, you can, for better understanding, the regression will be easy for you to quickly grasp the thing. Okay, you can see the linear relationship between the two columns, the variables. We used to call them as features. You can see the two relationship between two features. Okay, like linear, or they will be inversely proportional. Okay, so something like that. Okay. And data pre-processing once again. So this is the format which is cleansed data format. So the data set that we receive will not be in this way. So whenever you have them as an XML, that is going to be a structured one. Okay, so in order to not only the deep learning or machine learning will understand the numerics, it will also it will not it will it has no capability to understand the unstructured format of data also. Okay, we have to structure them in such a way and provide it to it. Okay, so two things are very major for deep learning and machine learning. Okay, the after the data that we receive, okay, we have some software, ISCX flow meter. Okay, if you give the data set to this particular software, it will convert them in Excel, XML, sorry. Okay, so that is the Excel, the format of Excel that you're seeing in the screenshot. Okay, so far any queries from anyone? Okay, so I'm just assuming that no one has queries. Okay, if you have any queries, please stop me at the point. Okay, so yeah, so here what happens is they are actually converting the data to an image. Okay, so in this way they can identify something wrong with the pattern. Got it. So you can see that there is some pattern. Every image in the below screenshot follows some pattern. Okay, so that's how it is. It follows some patterns. Suddenly, if that identifies something irrelevant, some portion of the image is irrelevant across the image. Okay, on particular part of image, then it easily alarms that there is an issue with the data. There is something issue with the network. Okay. So, you can see that, right? So you can see that they are mentioning that NumPy array of 50 cross 50 cross 3 dimension. Okay. So every data that you are supplying to deep learning or machine learning, they have to be in a structured. They should have some dimension. Okay. Without any dimension, you cannot do that. Okay. So the data that we got in the previous slide is changed to this image. Okay. So there are several ways handled, several methodologies handled to convert the data to an image, to the image that you are seeing in the slide. Okay. So yeah. So let's go to the next slide. Okay. So this is very important thing. Okay. Very important thing, and also very familiar thing in the world of deep learning. Okay. Which is part of a computer vision. We are the one that you are seeing is the computer vision technology. Okay, so the computer vision, what the computer vision is used for? Computer vision is used for predicting something from an image, okay, or video. Video, once again, it's kind of a frames, right? Every frame will be an image. Once again, the image will be supplied to the computer vision. Okay, So you can just ask a question, okay? What is deep learning and what is computer vision? Okay, so I can say deep learning, okay, is the very core part, okay, of neural networks. And whereas VGG 19, it's a network, okay, it's kind of architecture, okay. Before we give the data to the deep learning model, this is what we do in computer vision. So whenever you get a data image, or let's say if you're working on Facebook, working for Facebook, okay, you have to analyze that image, okay, for the face detection. Let's say my particular my photo is on some I mean will be there in my profile, right? Or my photo will be there with my friend profile, okay. And you might have known that it easily identifies the face that and marks me as Prasath. So I'm not going to the Facebook, okay. I'm saying this is the photo of me when I'm went to my friend's marriage, okay. This is photo of me when I went for a tour, okay. This is the photo of me when I walk, and which is taken behind the, I mean, photo has been snapped before, allowing me to walk, and it has been snapped behind me, okay. So there are several ways, okay. So I can while I'm talking to my friend, one particular from my left hand side. So all these things, am I audible?
Yes, Prasad. Yes.
Yeah. So all these things is challenge to the machine learning model. So I'm not, as I told, I'm not going to submit all my photos, all kind of permutation and combinations of my actions as an image to the Facebook. So you might have surprised at how it is predicting correctly, how is identifying your face correctly. Okay, so that is a beauty of deep learning. So it learns the data, okay. Whenever your image is there with the machine learning model, sorry, deep learning model, it identifies, it gets some embeddings out of it, okay. It will not take the entire photo of you and traverse through each and every pixel of you and check that Prasad's eyes will be in this pixel format and eyebrows will be in this format, okay. So it captures it, and it does some techniques, okay, to uniquely identify my face. So going forward, if I submit my I mean if I submit an image which I'm talking to my friend, okay, which is taken, and the photo is taken by the photographer when he's standing right to me or left to me, okay, it try to identify some uniqueness with my face, with my image, okay. By that way, it identifies the one particular person correctly, okay. So likewise, whenever you get an image, okay, to the deep learning model, what it does is it will identify the patterns, okay, inside it. There also, I mean, as I told, embeddings is one way, okay. Embeddings in the sense, it will not capture the it will not traverse through entire pixels of my image, okay. It will try to identify some points that is unique on my image, okay, and stores that as a embedding, okay. We used to call them as vectors in technically, okay. So now the VGG network, we come to VGG network, okay. What it does is, okay, so before VGG network, I'm telling this is a convolution neural network, okay. What neural network is, once again, every deep learning is part of neural networks, okay. The one that you are going to see is one kind of a neural network, okay. And the VGG is part of convolution neural network. What is a convolution? Okay, what it does is it reduces. Let's say if you, I mean, that nowadays the photo qualities or video qualities are increasing drastically. Okay, so by the way, the number of pixels for a particular image or video or video frames, it is going on increasing. So we have to take some action, okay, to reduce it, because even machine learning is feel hard to process the I mean that big image, okay, while predicting or while learning, while learning and building the algorithm. So what it does is it reduces the dimension. Okay, so if I, let's say I have a image of cat. Okay, what it does is it will reduce the pixels in such a way, okay, it can, let's say the dimension of, you have the image dimension of 400 cross 400, then it will be reduced to 100 cross 100. Okay, but that 100 cross 100 will have some data loss, but still the machine learning, we will supply the relevant information to the deep learning algorithm. So one that you are seeing is called VGG network, which reduces the dimension of the particular image before supplying it to the deep learning model. Okay, so there is idea called a methodology called max pooling. Okay, so that is in-depth concept. I'm not going to cover that now because it will be out little bit out of the topic. Okay, I'm just giving the overview now. Okay, now at the last you can see that multiple boxes, right? So they are the nothing but the dimension of the image. Okay, finally you can see that they are giving some dimension to the deep learning model. They might be in two-dimensional format or three-dimensional format. That depends upon the problem statement. Okay. So then after giving, extracting this dimension, it will be supplied to the machine learning model. So, now you understood that we receive the input. As I told already, the deep learning or machine learning model will only understand the numerics, numbers, right? So in that case, the VGG network receives the image and reads the pixels in the way of in the manner of numbers, okay, and finally it gives the matrix. The technically speaking, it's a matrix. Okay, it may be a two-dimensional matrix or three-dimensional matrix. Okay, and the machine learning model will take this matrix and do some do some learning about it. Okay, so you see here the training phase, the phase where a profile of normal payloads is created. Okay, so here normally any anomaly data is not needed for training, as the IDS will instantly discard any data with smallest. Okay, yeah, got it. So this is a beauty thing here. Okay, we want to let the system, the deep learning model, to learn only the normal data, because whenever the abnormal data, the anomaly things happening here, so you will have the, previous slides we saw that everything is converted as an image, right? So you will see something, the improper pattern with the image. Okay, so that's enough for the deep learning algorithm to say that there is some anomaly. It has detected some anomaly. Okay, so it has detected something anomaly. Okay, something phishing. Okay, so yeah, testing phase. What they're saying is we are yeah. Okay, so testing phase you can test with some improper data. You can have some sample of how can I say the abnormal data. So that the system identifies the anomaly things happening inside. Okay, so that's how it comes. So here what happens is, see here, every machine learning or deep learning will not give 100%. Okay, so here in this case, okay, we are only learning the normal payloads. Okay, so what happens is it learns with the 100% accuracy. Okay, and identifies, in the next slide I can show that it identifies the 80% accuracy of how can I say the anomaly data. Okay, now you got right. So the training data will have only the normal data. So whenever you give a machine learning with imbalanced data set, now the thing here is imbalanced data set, but this problem statement, the imbalanced data set is acceptable, because we like to learn only the normal data. So whenever there is a anomaly data, it reduces. The prediction accuracy will be reduced. Okay, and it will easily say that the data is data is anomaly. Okay, so something like that. So here in this case, it will say 100% accuracy. What happens is in real time, okay, in any other machine learning, the 100% accuracy will not be acceptable, and it will be definitely overfitting the algorithm. Okay, overfitting in the sense it will have the better accuracy while building the model, but while prediction it will not give the better accuracy. Okay, means that it has studied only the one portion of the data. The partial data itself. Now in this case, the 100% of data is reasonable here. Okay, so now in the next slide you can see that the anomaly data with 80% accuracy. Got it? So this is how it happens. And you can see that number of epochs and accuracy. So I mean, I don't have that deep neural network image on my slide. Okay, you can check offline that how the deep learning neural networks look like. So and quickly check that what is epoch. Epoch is nothing but you will have set of neurons. Set of neurons in the sense set of algorithms. Once this one way of algorithm is completed, we will get the data output data, and once again we feed them into the input. Okay, so it's kind of a looping for multiple times. So number of epochs is nothing but it's kind of a back propagation. Number of back propagation occurred with the neural network. Okay, we used to feeding the in output to the once again to the input phase is nothing but back propagation. We used to say that back propagation. Okay, and number, let's say if you are going to iterate for 2-3 times, we call them as epochs. Okay, so if you are going to iterate for 2 times, then the number of epochs will be 2. Okay, so see here, number of iterations increases, the accuracy increases. Yes, so deep learning model will learn the output. Okay, will have the output data once again fed as input. Okay, by that way it reduces by its own, okay, to give the better accuracy. Got it? Let's say if you are going to write an exam, okay, you are giving the submit the paper to the HOD. He is correct. He will. I'm sorry. He will correct your paper and give some marks. Okay. If you don't get any feedback, you will not learn. You will not give the better accuracy. You will not get better marks in future. Okay. What he does is, okay, you have to correct the. I mean, you have to work on the theoretical part or multiple choice questions, you can say. Okay, so that you can focus on that and you can give better output. This is just an example. Don't compare everything that with the deep learning. So deep learning, everything reads the data as in a numerical format. Okay, just an example I'm telling you so that you can better understand. So reason why we are giving the back having the back propagation is we have to make the deep learning to learn, but to learn better. Okay, so that it can predict better. Okay, and one that image that you are seeing is precision, recall, FN score. They are the metrics for identifying the accuracy. Okay, so in the imbalanced, if you have the imbalanced data set, let's say there is 100 data set and you have 70 female data set and only 30 male data set, male data. Okay, and what happens is in this case FN score will help you, because if you check the accuracy, the female data input will have the better accuracy while the male data will not. Okay, in that case you have to check the accuracy with the help of FN score. That is how it comes. Okay, and these things can be extracted using Python library, both the chart, the graph, and the accuracy metrics that is on the right hand side. And this can be easily extracted from the using Python library. Okay, so let me quickly go about the malware. Okay, malware is a malicious software that is that went inside your network or inside your device, everything. So I'd like to give a quick example. Okay. Okay, so I'll be done in 5 to 10 minutes, maybe 5 minutes. Yeah, sure. So what is malware? Yeah. Okay, so if you recently you might have heard about the WhatsApp attack. So what happened is, technically I'm speaking, okay, you will have some functions whenever a call is, whenever a person is calling you, okay, technically it calls some method, okay, it sends some packets to the client, the receiver, okay. So once the receiver receives the packet, we will have some functions inside it. Let's say I have an integer function, okay, which will occupy, which will receive arguments in 4-byte format. Okay. Now I'm usually sending the packet, okay, with the help only 2 packets. With the size of only 2 packets. So the attacker may take advantage of the rest of the 2 packets and insert some malicious code inside that and call your call the receiver. Call particular person. While calling, what happens is the unauthorized insertion of particular program inside the packets will go inside the client of the receiver phone. Okay, and only the call is enough. You no need to attend the answer the phone. Okay, only the call is enough. Only the missed call will be enough. So suddenly the malicious software will get a chance to be deployed inside your hardware, inside your device. Then it does several things out of it. So that is the thing here. Okay, so the way I mean the thing that I explained is it's one way of malware attack. Okay, there are several ways. Why I like to highlight here is there is a very recent one happened. Okay, in the world of how can I say secured cyber security. Okay, so why it is important? Yeah, as I told, right? So your spam emails or unauthorized calls. Okay, so everything is important to us, right? So we'll not. I mean, we are not rich that rich. Okay, we to buy every. I mean, to buy the mobile phone every day. Okay, we have to check our even the multi-million will not do that. Okay, we have to protect our our properties. Okay, technical problem, hardware properties or software properties. Okay, so once again, as I told in the previous slide, we have to generate the image in the same way. Okay, and it has certain dimension. Okay, here 256 cross 256 will be the dimension. The preparation of data set, once again, validation and train. Okay, I explained this already. Okay, same thing will happen here. Okay, and finally, so there are several IDs. So, it's not something like you have to only use Jupyter Notebook. Okay, which is here. Okay, you can do multiple IDs. That's your wish. Okay. And yeah, creating the model. Yeah. So now you can see that the just 4 lines of code, you can see that create underscore CNN, right? So that's a function. So I don't have the function code inside the slide. So if you go and check the method, I mean line of codes inside the create underscore CNN, they would have created the convolution neural network. Okay. So I mean, one example we saw is VGG 19, right? So quickly go to the slide. Yeah, here VGG 19. So likewise, the one more kind of CNN is used here. Okay, to predict to build the model and to predict the um, malware detection. Okay, yeah. Sorry, to identify the malware detection. Yeah. So here is the image once again. We used to generate the image in this way. In this algorithm, they have done in a different way. Okay. And the previous algorithm, they have created image in might have created in different way. Okay. So it varies the person to person. So how we are going to generate the image, it varies person to person. There is no universal methodology that this is the way you have to create the image. Okay. So that's not fixed thing. You can do your role. And finally, this is this is one way of learning rate and loss graph. Okay, you can see that loss is reduced. Okay, as I told, right, the deep learning will have the back propagation. Okay, what happens is when it's run for the very first time, what happens is the loss will be too high. Okay, probably. Okay, and while the number of epochs is going on, with minimum learning rate, the loss will be reduced automatically. Okay, learning rate, I don't want to confuse you at this time. Okay, because it's nothing but, okay, how fast you are fine tuning your loss. Okay, so that is a hyper parameter for deep learning. Okay, and with the help of the learning rate, you can make the model quickly or quickly understand the pattern and build the model. Okay, and so learning rate will it should not be higher. Okay, sometimes it will not stop at the right place. Okay, learning rate should be minimum, always minimum. Okay, so minimum in the case, some for some algorithm it may be 0.02, some algorithm it may be 0.01 technically. Okay, so that's up to the I mean data scientist or person, machine learning engineer. Okay, or the person who is writing the algorithm. Okay, and so whenever the learning rate we are back propagating with the help of learning rate, you can see that losses keep on reducing. Okay, and let's say if the loss is 0.020, we will stop at that and we will extract, I mean we will be done with the model building. So that particular model will be used for the prediction. So whenever the point at which the loss is less. Okay, okay, point at which the loss is less, we will consider that particular spot, and uh, we will stop at that particular point, and we will get the model build. Okay, and we use that for the prediction. Okay, Then yeah, so that's the conclusion. Okay, so yeah, from this study, it's clear the most of the deep learning algorithm comes up with better accuracy. Okay, yeah. So deep learning has this style of, um, I mean, managing the. Let's say if you are going to check with 4 features, you can do that. Okay, if you want to check with the 10 features of the total data out of total data set, you can do that. Okay, and you can reduce. There is a technical term called neurons on layers. Okay, so you can reduce them if you want. They are called there is a method called dropouts. With the help of dropouts, you can reduce the you can toggle the deep learning model. Okay, but if you are going to do that with the machine learning algorithm, you have to write the code for everything. Okay, but with the deep learning frameworks like TensorFlow, okay, these things are available already. No need to bother about it. We have to just set the arguments. Just you need to just configure the neural network. That's all. Okay. So, and the final thing is the deep learning will be always useful when the data is large. Okay, not only in the field of the cyber security, it is global. So whenever the data is huge, okay, the deep learning model will give the better results when compared to the machine learning, traditional machine learning models. Okay, that's all about it. So do you have any questions?
Any questions? Any questions, participants? Participants side? Okay. Uh, Thank you, Mr. Prasath, for your wonderful session.
Yeah.
For in the insight of deep learning in the cybersecurity field. I hope that all the participants get a good learning experience in the real-time experience in the field of deep learning,
Mm.
and also get some ideas about how to write the coding and some of the coding in the deep learning field, getting all the ideas in the field of deep learning and cyber security.
Mm.
Thank you, Mr. Prasad, for your wonderful session. Okay,
Yeah. Thanks,
all the
Anand. Thanks. And
yeah,
yeah.
yeah. Thank you, Prasad. Okay,
Yeah. Thank you, everyone.
all yeah, all the participants wait for some more minutes. Other speaker will join after 5 minutes.
Okay. Thank you. Thanks once again, Anand, and everyone. So I'm dropping now. Is that fine?
Yeah, yeah, yeah.
Thank you.
Participant will wait for some more minutes.
Okay, dear participants, we'll start our next session at 11 a.m.
Hi, Anju. Can you hear me okay?
Yes, sir. Yes, sir. Okay, then shall we start, sir?
Yeah, absolutely. Absolutely.
Okay, 1 minute. Okay, participants, we are going to start our next session. Good morning, all of you. It's a great pleasure and for honor for me to extend a hearty welcome to all of you for the 6th day forenoon session of STTP Phase 3. Myself, Anju, Assistant Professor from the Department of Information Technology. Today we have a knowledge enabling session on Senior Solution Architect. We have an eminent speaker for this session, Mr. D. Minu Karthik, Senior Architect, Amazon Web Service, Dallas. He has done his Master's in Computer Science and has 17 plus years of industry experience. Mr. Minu Karthik primary area of interest include helping customers to build and scale highly available, distributed and secured cloud infrastructure. On behalf of management of KCT College of Technology and Department of Information Technology, I welcome our speaker, Mr. D. Minu Karthik, for this session. Welcome you, sir. Now the platform is for you.
All right. Thank you, Anju. Good good afternoon. I think it's almost well, actually, good morning to you all. My name is Manu, as Anju mentioned. Quickly wanted to, before I start sharing my screen, wanted to thank you all for taking the time to listen to my talk today on a Saturday morning. So I certainly appreciate that and appreciate the opportunity to be here. Give me 5 seconds maybe. I'm going to share my screen so you can look at my slide deck and then we'll go through
Sure, sir. Sure.
topic of the day. Share screen. All right. I'm going to turn my video off. That way it's not, it's not mucking with the bandwidth here, right? So I'm just going to quickly turn it. I apologize for the mess here. Just going to hit F5. Okay, cool. All right, can you guys see my presentation slide? Maybe Anju, can you?
No, sir. The screen is not shared so far.
Okay, great. Okay, how about now?
Yes. Now it's good.
Okay, perfect. Cool, let me turn my camera off. figure out. I apologize. We don't use Zoom in my office, so I'm struggling to figure out how to turn my camera off. Stop video. Okay, there you go. Okay, perfect. Awesome. Cool. Let me do a quick time check. We are about a minute into the talk here. Okay, so quick intros. Yeah, once again, Minu Pandey, Senior Solutions Architect. I work for a company called AWS, Amazon Web Services. It's part of the Amazon.com, the retail company. So one of the divisions of the company is our cloud computing division. That's who I work for. And primary role is essentially to help customers basically build applications, modern applications on our cloud platform. That really is my day job. I am based out of Dallas, Texas in the US, and the current time is 11:31 p.m. If anyone is curious, I'm about 11 and a half hours behind you guys, Friday evening. Welcome to my session. So today's session, Frank requested that I talk about security best practices using AI technologies, right? Security is a big business. Security is a huge industry. It's almost considered a vertical, but technically it's more of a horizontal if you think about it. No matter what you do, security is a sort of an integral part of what you want to do, even if it's application development, if it's infrastructure, if it's pretty much anything that you do today in the world of computers, security is sort of like part and parcel of that journey. There are plenty of ways we've been doing security ever since computers have come into existence to sort of protect either the machine that you're running your applications on, or either protecting the applications themselves, or protecting the data that these applications typically hold. Right. So plenty of methods that you typically use. People often talk about preventive. People talk about detective methodologies where they implement security features and functions to sort of like, figure out if something has happened or stop something from happening before they happen, things of that nature. But as we have progressed in the last, I want to say about 5 to 7 years, AI has really, artificial intelligence has really taken a center stage in all of the things that we are pretty much doing today, right? We are talking about autonomous driving. We are talking about, voice assistants that are living in our household. They basically augment our lives with, they do simple things like we have robot vacuum cleaners that can actually see what's in your house, navigate through your living room and whatnot, and avoid obstacles and all of those things. They're basically, deep learning and artificial intelligence and machine learning are put together to create these robots. So one of the recent developments that has been happening in the industry is using artificial intelligence in the world of security as well, right? Because the amount of data that we are trying to secure is massive. The velocity of the data that is actually changing is also massive. And of course, the networks that we are actually hosting these, this data on top of, that is also changing constantly and evolving constantly. So it's really, really hard for a human being or a bunch of human beings that work in an organization to have an eye on all of these changes that are typically happening and be able to protect it. Right. And sort of like proof is in the pudding, we often read about it in the news that there has been a security breach, somewhere, right? So a lot of these things are happening all the time. Recent example is, the allegedly Russian hack of a bunch of, U.S. Government data related to solar winds that happened a few weeks ago, right? So that is really the topic for today. And what I wanted to talk about is, this is a vast topic. It's really, really super hard to hone in and talk about, all of the things that are out there. So I wanted to pick one single, group within Amazon Web Services. The group is called Automated Reasoning Group within AWS. These guys, the colleagues that work in this division, they came up with this automated reasoning to protect the data and protect the networks that our customers run on top of AWS network. To be able to do that, obviously, you needed to think out of the box to be able to go protect massive number of customers. We have literally have millions of customers that run pretty much across the globe, and they do it 24/7. So companies that you may have heard of, Netflix, Amazon Prime, Capital One, lots and lots of companies that run on AWS. How do you come up with a technology that applies to pretty much everyone, right? Netflix alone is a massive company in itself, and that's just one single company out of the millions of customers that we have. How do you come up with a technology that can be applicable to pretty much across all of the customers that is running on top of this cloud platform, right? That was the challenge they were really presented with. And they basically thought of, yeah, this is not a problem that we can employ a bunch of people. We cannot keep hiring tens of thousands of people because you will run out of people that are able to go do this. So they wanted to come up with a automated reasoning technology that they really wanted to deploy, right? That's what we are going to talk about. It's barely scratching the surface of artificial intelligence in the security field. And the talk, the discussion, the talk today is a little bit of a philosophical talk. And I say philosophical as we go through it, you will understand it, because obviously it involves a lot of mathematical computation and what really goes behind the scenes for creating security that is based on AI, right? So that's what we are going to look at. But before we start diving into the automated reasoning technology that AWS really employs, I wanted to sort of like level set some of these things, in terms of security. How do we really define security, right? So it's a really good question, right? So secure is basically nothing bad really happens, right? That's pretty much secure in the world of computers. I can't think of anything bad happening to my computer. So that's basically my computer is considered, secure. Another way to define it is as long as, whatever I'm building, as long as my customers are not calling me or emailing me and yelling at me, that's pretty good because things, whatever I deployed, whatever I gave to my customers, whatever I helped design, it's still working the way it was intended when it was originally created, right? Of course, my boss keeps paying me, then I know I have a job and I'm getting a paycheck. Okay, nothing has happened. Otherwise, I wouldn't be getting a paycheck. All of these things are basically secure in some way, shape, or form. My job is secure. My customers are happy. Of course, things that I gave them, they're also good, right? But the wrong, the things that go wrong did not happen, but good things all also happen with this, right? The wrong things don't happen, but the good things do happen, right? So that's basically secure, right? And so the other question is on the system side of things is the system only has this desired behaviors, right? So I designed a system and I basically said this is how I'm going to design a system. This system has 10 servers and all of these servers have a very specific functionality, and all of these servers will always perform the exact same things that I asked it to do, right? So that is also how we define secure, right? And the other thing is, are they all in a reachable state, right? These servers that I put together, are they all in a reachable state, right? Can they, after processing, pretty much anything that I throw at it. Let's say I have a web server, right? And what does a web server do? I have a bunch of web pages. The web server's sole purpose in its life is to basically
process those web servers. And if someone asks for www.whatever.com, it's just basically going to throw at it, right? That's what is, that's how we define that state of that web server, right? So I'm basically saying, go ahead, host these web servers. As long as you're hosting these web servers without any hiccups, I'm going to call it secure, right? And how do I really test for, security, right? So I'm supposed to secure all of these servers that I gave you. How do I really test it? I can do threat modeling, time-honored tradition of penetration testing that people often do, right? You can hire a bunch of penetration testers or pen testers, and then you can have them, hey, come out and say, you must have watched it in a bunch of Tamil movies too, right? There was a movie in which I forget the actors, Ajit and I believe Arya. Arya is like a pen tester, if I remember correctly. Right? So you can hire a bunch of people, ask them to say that these are the states that I defined for these servers. Can you go ahead and get creative and see that, do some penetration testing and see how it works, right? And then, of course, the other thing that you can do is fuzzing as well, right? Fuzzing is basically, I don't know if you guys have heard of this term. Maybe, I'm sure you guys have heard of this term, but basically, since we are level setting, fuzzing is basically, if something was intended to do something, let's say you have a, I don't know, an oven. And if an oven is only supposed to bake food, if you wanted to test an oven, maybe you take a bunch of batteries and put it in the oven and see what happens in that point, right? So basically you go off of the norm and you do something completely different from the set parameters for a certain system. You go outside of the parameter and see how that system really behaves, right? So that's fuzzing. But then fuzzing has its own, limitations as well. Like how much can you throw at a system that is completely, outside of its norm, right? So finite number of things. Maybe if you have more money and more resources and more time, maybe you can throw more things at it. But then again, it is still finite, right? So how do you build a secure system, right? If you have a single system, you start simple. It's pretty simple, right? You have a computer. You don't really expect the computer to do unexpected things because it's an inanimate thing. You tell the computer to do a certain thing, the computer does that, and the computer will keep doing it as long as it's alive for the next 100 years. If it's still there, if it's still running, it'll keep doing the exact same thing for you, right? Absolutely no issues. It's super easy for me to go and secure the computer. Maybe I have to take the computer, put it in a room, lock up the room, and then maybe I have to make sure that there's some antivirus or whatever is running on it. I can secure that computer. But what happens when you introduce a human element to that computer? Maybe that computer is supposed to be used by, let's say, 10 different users. And once you start involving humans into this chain of computers, then the predictability, the behavioral predictability of that system really goes out the window, right? Because you cannot expect humans to be predictable. Either by design or by accident too. Someone can make a mistake accidentally, or someone can make a mistake maliciously to sort of like cause harm, right? So those things can happen when you start introducing humans into the picture. So that's your first sort of like wrinkle in the equation when you're trying to secure a system. And of course, all the systems that we have today in this world are pretty much operated by humans in some way, shape, or form, right? Then what happens? That's a simple system, a single system used by 10 users, but then that's not how we really operate in this world. You've got a bunch of computers. You're going to network all of these computers. Of course, the humans are still involved, right? Then you start running into other problems, right? Did I give this particular person the right level of access? How do I know that, no one actually changed that access? If you have a lab environment, right, you have professors and you have students and you have lab assistants, and then you have like external parties, guests that are visiting your lab, visiting your university and all of that stuff, right? everyone gets their own level of access and someone has to maintain it. And then you have to have a certain level of trust to say that the network admin, the systems admin, the security engineer, all of these people are actually implementing what they are implementing, right? What if someone walks away with a hard drive and that hard drive has a bunch of questions for an upcoming exam or something like that, right? A bunch of things can happen. So basically, the complexity starts to increase once you start to network computers and once you start adding more and more humans into, into the particular equation, right? Here's a very simple system, right? So here's a typical boxology, if you will, right? You've got the internet on the left-hand side, and you've got a bunch of web servers, and then you've got a bunch of backend servers that are connected to the web server. I hope everyone understands what a bastion host is. Basically, the orange lines indicate how you would actually access these backend servers, right? So fairly simple diagram. I can look at it. I can basically say, yeah, the traffic is flowing exactly the way I intended the traffic to flow. And the web servers really don't have, or the internet does not really have direct access to these backend servers. If you have to get to the backend servers, I have to go jump onto this Bastion server or jump box. And from there, I can actually jump onto this SSH tunnel to these backend servers. It's pretty simple to do, right? I can look at it and I can say that. But of course, you keep adding complexity, right? Things start changing, right? You may at some point hit a stage where you want to troubleshoot, all of these systems are down and you wanted to troubleshoot something. Then you bring in a random server into this environment because this Bastion server just went down on you. You can't access it. You just introduced a random server. Now you basically altered the entire setup, right? And you call it, let's say you keep it under Frank's desk because it's a secure place to leave it under. So you just leave it there. And then you say, okay, this is just a temporary situation until we fix this thing. And then we'll get rid of this, right? But typically what ends up happening is that temporary situation could be a number of weeks or months or sometimes years. This happens quite often in the world, right? People introduce something, they probably worked for 17 hours to fix this thing. And they said, yeah, I worked way too much. I'm going to go home. We'll come back and, restore, we'll shut this random server down tomorrow. And then they leave and then they forget about it. That thing is sitting in there. Now you're basically introduced a random server into this entire thing and no one really knows about it, or maybe someone knows about it, but they don't care enough to fix it, right? How do you detect for some of these things, right? Times 10, times 100, times 1000, if you can amplify those mistakes, how do you actually figure that out, right? Imagine this is actually a real picture that was basically we got it from University of California in San Diego. This is just a sliver of the internet. These are a number of nodes. This is zoomed out really, really far away. This is basically a sliver of the internet that you're looking at. It's fairly impossible to, say that where that random box is or where that mistake that you made in the internet if you're running a massive enterprise application, which we do for Amazon.com, right? There's a whole bunch of stuff. How do you track all of those things, right? So that's why really the advent of AI started coming into existence, right? And networks are really not that special, right? We understand networks pretty well. Everyone knows how networking works for computers. You've got permission policies. You've got interprocess communication that happens between nodes that are sitting on network, and once they get to those particular nodes, they're executed by some sort of code, which could be a TCP/IP protocol stack. And then it gets processed and gets back out into those, these networks that are connecting these nodes. And it doesn't really apply just to computers, right? Electrical systems are pretty much like networks. Vehicles, if you want to consider, they're not, I'm not talking from a network standpoint, but again, they're not something, that we consider special. We understand all of these things pretty well, right? But the challenge with all of these things are they're constantly changing, they're constantly evolving, right? If you ever bought a vehicle, the minute it rolls out the factory and you buy it, you start making changes to it. Maybe, you go and change the horn. Hey, this horn is not too weak for my Chennai traffic. I'm going to change the horn. I'm going to add a bunch of lights to it. You start changing it, right? So some of those changes are, immediately visible. Some of those changes are not visible. You'll have to go underneath the covers to figure that out. And once you sell that vehicle, the other person has absolutely no idea how that vehicle works or what changes have been made to that vehicle. This is exactly what happens in a computer network in an enterprise, right? Things change, people leave, new people come in, new people make changes. Not all of those changes are recorded, right? How do you keep track of all of those changes when it comes to security, right? Similar example for houses as well, right? So what do we do in such a situation? How do we really, figure out what is good security? How do we know that changes have been made, right? So the basic, the automated reasoning group, the basic thing that, that they did, and a lot of security engineers, of course, not just them that came before them, they try to violate some of these assumptions that you made for a system, right? If you said the system, has to operate at, let's say 100 packets per second, what happens if I pump 1,000 packets per second, right? You try to assume, you look at a system and you see how that system was designed, and you try to understand what the assumptions were made in the system to make it operate the way it really operates, right? So when you start violating those assumptions, that's when you really, start figuring out where the weaknesses are, where the deficiencies are. Like, how does the system respond, right? If it says, if you have a car and if you say you can't drive this car over a certain limit, when you start driving it over a certain limit, what are the things that really fail, right? Tires don't last over, passenger car tires, they don't last over like 130, 140 miles an hour. They start to overheat, right? There are plenty of things that can really go wrong, right? So that's how they really, they violate some of these assumptions. They violate the service envelope of the design of that particular service, right? So a good example of that is, I don't know if anyone can guess this. This is basically a SQL injection attack, right? SQL injection attack was first done by somebody that was really, really creative. I don't know if he was a black hat hacker or a white hat hacker, but somebody got really creative with the web form that said first name or name field. Instead of putting in their name, what they did was they actually executed a SQL query. They just put a SQL query that says drop table users. The system that was designed basically took that and basically sent it all the way back to their database, and then it dropped their users table. That's basically SQL injection attack, right? It's not a volumetric attack, but it is actually a very sophisticated, intelligent attack that goes after one resource. It goes after your database, right? It doesn't do anything to your web server, your application server, none of that stuff. It goes directly, gets executed against your database, and then it drops that. That's basically SQL injection attack, right? And so people get, really creative about this when you start pushing the envelope of what it was designed. So that's what we really say the state space, right? So what are all the different possibilities that are involved in a certain system, and what are all the potential values you can give it to that state space and see what happens to your system, right? That's really what is the exploring this state space really means at this point, right? It's a very simple system, right? You've got two variables, A and B, and the system is designed to basically increment A and increment B. That's it, right? It's gonna keep doing it until you stop that particular system, right? So you can basically keep doing it, to your heart's content, and you can basically imagine a state that can potentially look like this state where A is this massive number, 4,343, what is that? It's 439,023, and potentially 5 million for B. That is a state that you can potentially imagine because you keep incrementing and you can potentially arrive at that state. But that is not your entire state space, right? There is a state space that also exists that basically says, yeah, A could be 400,000, 439,000, but guess what? B could exist in a state called -1. How did that happen? We don't know, but that is part of that state space. You will never figure out how the system got to this unless you start pushing the envelope of this particular state and you start testing it in ways that you really go above and beyond the assumptions that you've really made here, right? That's really where fuzzing comes into existence. You're basically questioning all the assumptions and then checking to see what kind of crash do you really cause, right? Is this just crashing and going down and just affecting your availability, or is it really doing something else that could potentially affect your integrity and potentially affect your confidentiality of the data that you're storing, right? That's basically fuzzing, right? But can you guys hear me?
Yes, sir. Yes, sir.
Okay, sorry. Yeah, I thought it dropped here for a second. Okay, cool. Yeah, so basically, smart security engineers, they try to push it, the envelope of the system to see how it really reacts. That's where it really starts. And in this particular case, in at least our case, the automated reasoning group, this random server that we spoke about, I forgot to change the name from Joe to Frank. I changed it in the first one. But the random server, at least in an AWS environment, right, in the cloud computing environment, we don't really have there is the notion of a random server, but the way we actually envision all of these servers that are running in the cloud environment for all of these millions of customers is basically through what we call it, in the industry as an API, right? Every single object that exists on top of this cloud platform can be expressed as an API call. So basically, any customer that is operating on AWS can go execute a very simple API call and figure out what is running in their particular environment, right? So this is basically the genesis of, or at least the birth of the automated reasoning group, right? So they look at this environment that they want to protect, and they know this entire environment can be scripted in an API call or a bunch of API calls, meaning I can basically go, EC2 is basically a virtual server in the cloud, by the way. EC2 describe instances would basically give me all the EC2 instances or all the virtual servers that are running in a certain network, right? Similarly, I can do that for pretty much every single network component, every single network access control list, route tables, security groups, all of these things, I can go list them out, right? So that's really, what they envisioned, or that was the very first step in their automated reasoning group that they looked at, right? So even in that case, let's say, let's take a very simple example of a single customer, and let's just go through how their environment might look like for that particular customer. So accounts is basically number of AWS accounts that you have. Typically large enterprise companies, or typically companies, have multiple AWS accounts. One might be a production environment, one might be a development environment, one might be a QA environment, one might be staging. So they have multiple environments. So let's say, each of these accounts will have multiple networks. These networks will have subnets. Subnets will have access control lists. Access control lists, underneath that, you also have something called security groups. You also have route tables, which actually define how the packets must flow within these networks and outside of the networks. And then, of course, these networks also host servers. And then these servers have protocols. And then, of course, you have ports that live in each of these servers. So if you put a number for all of these things, random numbers, right? Let's say you have 5 accounts. Let's say you have each of these accounts, you have 3 networks. And then you finally come to the number of ports. Of course, 2 to the power 32, you have 665,500 and, well, 536 technically, if you include 0, right? So that's how many ports you have, right? So if you have to check what went wrong in all of these combination that you're looking at, you're potentially looking at close to 9 billion, close to 9.5 billion potential combinations, right? And this doesn't even include traffic coming into your from the internet into your network. If you start considering those sources, that's basically 2 to the power. If it's an IPv4, it's 2 to the power 32. That's about a 4 billion sources that you could potentially look for. And if you consider traffic going out of your network, of course, you've got anything over 1024 port number going all the way to 65,000. So this number is massively large, right? So it's impossible for a human to figure out what went wrong here. And even if you try to figure out, it would probably take months or years to figure out a single mistake, right? Again, how do you do that today? There are plenty of ways to do that today. One of the popular one is Stride. I'm sure you guys have heard of it. You know, you look at all of this traffic that is coming into your network, and then you try to classify that traffic. You try to classify those packets. Is it a spoofed packet? Is it, are we getting tampered? Sort of like a repudiation? Is it a denial of service attack? Is it an amplification attack? Is it a volumetric attack? Did I give someone, accidentally more permission than I did? You know, you could think of it a much, these are the major buckets that you would classify those threat models under, right? Can you do that? Sure, a lot of people do that, but at scale is the challenge here, right? When you start looking at massive scale, none of this stuff actually will fit, right? So that's really the genesis of they wanted to come up with a magic recipe where they really, wanted to automatically design a system that would look at a certain network, no matter what network it is, how the network was designed, because the networks are designed by these individual customers. They can design it any way they want to, right? So they wanted to come up with a recipe, a magic recipe, where you throw anything at that magic recipe, it'll basically try to tell you what is, if something is wrong, if something changed, if something was altered, then it would basically point out something has changed here, you should go remediate against that, right? So that's why they really wanted to come and do that. So we spoke about this, humans exploring the state space. Yeah, it could be fun, but it's super slow. Same thing, machines, if you were to go do that, which is how we do it, we have SIMs, we have IDS, we have IPS. Again, the scale doesn't match. It's faster than the human, but still slow, right? Modeling your system is the only way you can do this. When they say modeling your system, what they're really talking about is they know what good looks like. What I really mean by that is they know what a good network looks like. They know what a secure network looks like, right? They want to take that secure network, they want to create a model of that secure network and sort of like do a standard deviation from that model to say that this network, when we first created, this network was, I consider this secure. For example, the easiest way to understand this is think of it as a physical security. Let's say you have a bank. When a physical security inspector comes in and designs this bank, they exactly know what the entry points are, what the exit points are, how many of them are there, how many doors, how many windows. They know every single one of those points. And if they know all of the doors are locked, all of the windows are shut, shut, and then I have 10 doors and 10 windows, and if I go shut all the doors and windows, I know this particular building is safe, right? That is how they define that. They take that model and they basically say, this is good. And any deviation from here, if I find out, I take this, I compare it to the current state. 3 months from now, let's take a look at the same bank building. Someone threw a rock at the window and the window pane is broken. Now they take that and they basically say something has changed. I'm going to compare it to the previous model when I said it was secure, and let's see what the deviation is. 9 out of the 10 things that I said could potentially cause a breach is good, but there is one thing that is quite possibly could cause you a breach. Then I'm going to call it insecure, right? So it becomes a lot more tractable when you start, modeling your system. That is exactly what they want to apply here in a virtual network for security, right? But then again, it came with its own challenges, right? How do you, how do you know that you don't have too much detail, right? You have to have the right level of detail, right? You can't start throwing too many parameters at it, then you will never, figure out a solution for it. Again, too little, obviously, you're going to lose a lot of fidelity there, right? You don't know where the windows are, you don't know where the doors are because you don't have the blueprint of that building, and this is a massive building, then you're going to be in trouble, right? So you have to understand what your application is, what your network looks like, right? So again, goes back to the API that we spoke about. You can go look at a network. You can basically do a bunch of API calls, and you can really know what that particular network is really made of, right? So that's when they really came up with automated reasoning. And, it does, they wanted to, create 3 different states here, right? Or potential states that they wanted to define. One, what can it potentially do, right? And 2, sorry, the first state is actually what can it potentially do. The second state is what will they do, and the third one really is what will they never do, right? If you can define these 3 different things, then you exactly know if this green is the only path that is the allowed path, then you know that's the only allowed path. Every other path is red. You can't use that. But guess what? Someone could come in and basically make those paths all green, right? Because your network is designed that way. The access permissions that you have given potentially does that, but they may never be able to do something like this all red path, right? That's how the system is designed. So if you can figure out these 3 parts for your particular system, then you can potentially go create an automated reasoning that can actually help you make these determinations without any human interaction, right? So to visit the, to understand automated reasoning, they really go back and look at, this is Euclid, apparently, a famous mathematician from 300 BC. This is the guy famously that actually wrote a proof for the Pythagorean theorem, which is basically, he found out that the side opposite the right angle, the square of the side opposite the right angle is sum of the sum of the squares of the other 2 sides, right? The a squared plus b squared equal to c squared, right? Obviously, this guy, lived in 300 BC. This guy did not, have calculators or modern computers, or this guy did not even know all the laws of the universe at the time even, right? How did he really go about proving this is basically using known constant numbers, and he used geometry, right? You can draw a bunch of stuff, and then you can go measure that bunch of stuff, and then basically say, I'm going to keep doing this. And then he used mathematics basically to prove that. But Euclid's theorem has not been proved incorrect for all the triangles since 300 BC to now, until now, right? It still holds true. That's how he has given a proof. We haven't come across a triangle that really violates this law at this point, right? But he didn't use automated reasoning. He used unautomated reasoning. And that was really the birth of this, Boolean satisfiability or satisfiability, the concept, right? all computer programs, of course, are made of zeros and ones, and that in itself forms your Boolean logic. But the core challenge of Boolean logic is basically what they call it as satisfiability, or SAT. You guys probably know more about SAT than I do. How do you solve for this core challenge of Boolean logic for satisfiability? Is basically how do you satisfy a particular formula? The only way to do this is, the easiest way at least to do this is you find assignments in this particular formula, to make sure that you try a bunch of different assignments, and then you work backwards from the right-hand side to see what assignments will really fit this particular result I'm trying to drive here, right? That's what they're really working at, right? So they basically try various different assignments, and try to work sort of like backwards from that result over there, right? And this really forms the NP problem, or NP complete, the first known NP complete problem. Again, this is probably way out of scope, and you guys probably know more about NP complete than I do as research scholars. But NP complete is basically, the simplest explanation is there is a mathematical proof to say a certain problem is extremely hard, right? If someone comes and tells you that I have a really hard problem, you just have to take your word for it. But an NP complete problem is basically, if someone says this is an NP complete problem, that means that that particular problem has mathematical proof that it is extremely hard, right? So let's go back to this, the satisfiability problem here again. Why is it really a hard problem to figure out the assignments that will fit this result? Is how do I cause those results that I really want? That's what I'm really asked. That's the question I'm really asking. Again, in mathematics, the way that they did this was a little bit of over a bunch of time, sophistication, and writing a bunch of complex algorithms. They can basically solve this problem. And these algorithms that they wrote to solve this satisfiability problem is implemented in what's called an SMT solver, right? That's really what we are going to be using. Do you guys teach SMT solvers at your college? Or is that not something that you guys teach? No worries. We can continue, but basically this is the basic starting point for automated reasoning, and the usage of SMT solvers to figure out how can you actually plug in different values so that you actually cause the result that you want, you're looking for, right? So let's look at why this problem is really hard, right? So here's the state space, right? Since it's Boolean logic, it's all going to be zeros and ones, right? Let's say the state space is basically 20 variables, not very big, just 20 different variables. But guess what? For 20 different variables, you have almost 1 million different possibilities that you can write for 20 variables. 2 to the power 20 is well over 1 million, right? So that's how many possibilities you have to arrive at this result that you're looking for on the right-hand side, right? So it's extremely hard. When you go from 20 to 30, you all of a sudden go from 1 million to almost over 1 billion different possibilities, right? So it's extremely, extremely hard to solve for a problem like that, which is what exists in a network. We looked at the network, we already saw 9 million without counting like another 2 billion in internet traffic and all of those things. So that's an extremely hard, so that's why it's called an NP complete problem, right? But with the SMT solver, the way that actually that solves for the satisfiability problem is it works backwards from the result, and then it sort of like cheats, right? instead of working forward from constant numbers and then plugging in variables, it basically works backwards from the result itself, and then it tries to solve for the problems that you're really facing, right? So that's the SMT solver. That's how it really works. Again, it's just an algorithm, right? The satisfiability modulo theory. That's basically the SMT solver problem, right? Now, we spoke about the state space in the previous example, that those are all just a single variable, 2 to the power n. But in a network scenario, those are not simple, single variable, right? You have a bunch of formula that you could potentially implement. And stay with me here. This might be very abstract at this point, but what they really mean by this formula is each of these nodes that you might encounter in a network. For example, let's say you encounter a router, which is supposed to route at layer 3. You encounter, let's say, a layer 2 switch. Let's say you encounter an internet gateway, right? All of these things can be, expressed in terms of, what they do. Let's put it that way, right? A router is going to route packets, at layer 3. A switch has a specific function, and the switch is a layer 2 switch. So, it's not going to leave layer 2. So you exactly know that's what they really mean by these formula that they are saying. But it's still more complicated than just a 0 or 1 variable. There is a formula behind it, right? If a packet comes in, I have to go look at a route table, and I have to match a network ACL. And based on those two things, I have to take this packet and go to this next node, as defined by the route table and as defined by the network ACL. That's how a router is going to make a decision, right? That's what they mean by these formula, right? And this is not just implemented in, this is getting into network security and security in general, but this has been implemented in plenty of other areas already, right? They do this in manufacturing, in military applications, aerospace industry. They do this in TPM type hardware that's found in pretty much all the computers, CAT scan type environment in medical industry. And of course, we started using that in AWS right now. Right. So we started this maybe about like 4 or 5 years ago. Right. So how do you actually reason? We spoke about all the abstract SMT, all of that stuff that, that you have to use for artificial intelligence to go look at the network. So let's actually look at a network and see how it really works. Right. A very simple 3-tier application. You've got web, app, and database boxes, right? 3 each of those. And then you've got internet on the left-hand side. You have to basically bring this application live on the internet. What do? You put them in a network, and then, you segregate all of these different layers of servers based off of their role into their own little subnets. And then you add, let's say, network access control list, right? So basically you say that web servers can talk to application servers, and application servers can talk to database servers, but web servers cannot talk to database servers straight up, right? So you make some conditions, you put some conditions, and then of course you connect the web servers to the internet gateway, and the internet gateway is directly connected to the internet. This is a very little setup. You just, you just started a company, you set up this network. But then, of course, it's super easy for you to manage. You're managing it. But what happens, right? You start growing. You start adding more networks. You start acquiring companies. They bring their own networks. You start connecting all of these networks together. You end up with a massive, network that you have absolutely no idea how things are connected in that particular environment, right? So it keeps growing, right? So once you get to this point, how do you know that you actually built the network the way it was actually, hang on a second, my PowerPoint crashed. I apologize. I hope it saved it. All right. Can you guys see my screen? We good?
Yes, sir.
All right. Perfect. Perfect. I apologize again. But going back to this slide, so massive network, right? You have no idea that your network is exactly the way that you built it. You've hired a bunch of people, right? So it's absolutely impossible for humans to actually figure out it's the way it actually, you built it, right? So how do you actually figure out, it goes back to the modeling that we spoke about, right? You know what a good network looks like, because you know what security for your network really means, right? It could basically mean protect, you can give direct internet access to, let's say you store credit card data, right? So if I'm storing credit card data in a database server, I know that database server could never have direct public access to the internet, right? So that's basically, that's how you define. So that's just one rule. You could have 1,000 rules like that in your particular network, right? So you take snapshots of these networks, right? So instances are basically servers, right? So you've got two servers, and then those two servers, both of them are actually in a subnet, right? And the subnet has a route table, meaning the route table is the one that's going to say, how do you route this traffic, right? That's going to basically tell you if a packet comes in, where's the next hop? Where should I go, right? And then you take that subnet. That subnet basically lives inside a VPC is basically a network, a virtual private cloud. It's a network, right? And the network is basically attached to an internet gateway, and then internet gateway is attached to the internet, right? So this is what you have, and how we looked at it was we said, okay, we know what a good network looks like, and we know what a good route table looks like. We know what the server A should do, server B should do, right? So we just spoke a whole bunch about SMT solvers, where we actually, this is the state space, right? So the right hand side is the state space, right? We spoke about that 2 to the power n, and we said the state space have multiple formula. So take that state space and you're talking about, hey, this state space, I'm saying this is a network. This network has all of these things. Why don't I take this state space and why don't I apply it to an SMT solver? Because you just told me this SMT solver is this brilliant little algorithm that can actually, work backwards and tell me if this is a good network or not, right? But what ends up happening is an SMT solver in itself is just a basic algorithm. It doesn't really know, it only knows zeros and ones, and it's just an algorithm. It doesn't know what a network is. It doesn't know what an internet gateway is. None of that stuff the SMT solver knows, right? And of course, that's where people like yourselves, come into play with PhDs and double PhDs and whatnot. You are basically a secret sauce that's gonna basically make sure that the SMT solver understands what a computer network is, what an internet gateway is, what internet is. That's really what they're doing in this AI security. And the way they do this is they're basically converting this network, this access control list, security groups, and whatnot into. I'm sure you guys have heard of a graph database. I'm sure you know what a graph database is. You know what a bit vector could be, strings and integers. So basically convert all of these complex networking terminologies into graphs and bit vectors and strings and integers. That is basically the world where an SMT solver lives and understands, right? And that's really the secret sauce that goes behind converting all of this stuff, making sure this SMT solver understands what a network does, what a route table does, and then let the SMT solver tell you if you have deviated from your model secure network or not, right? So in this case, you take this particular network and you start representing it individually as nodes, right? And all of these nodes, so this is basically a graph database type representation, right? The simplest way, the easiest way to explain a graph database, the very popular application that most likely uses a graph database is Facebook, right? Facebook was actually one of the pioneers of graph database. Graph database really came into existence sometime in the mid 2000s, right? Facebook started working on maybe 2003 or 2004. They looked at a traditional relational database, and they said, this sucks. Traditional relational database is not going to work for the type of application I'm building. So I have to build a brand new type of database. At the same time, Amazon was working on something called NoSQL, right? We have a product called DynamoDB, and there's a guy by the name Werner Vogels, who's our CTO. He wrote a white paper on DynamoDB, right? And DynamoDB white paper eventually got spin-off as MongoDB, React, Cassandra, Couch, you name all these NoSQL implementations. Similarly, graph database was basically pioneered in some extent. Of course, academia played a big role in all of these things, but basically they represent as nodes, meaning Frank is a friend of Minu. Minu knows Sri Vivek. Hey, guess what? Should I say, since Frank knows Minu, Minu knows Sri Vivek, let me say, hey, Frank, do you know Sri Vivek, right? Or there could be a bunch of other nodes. Frank went to MEPCO. Frank is a friend of Minu. Minu is a friend of Frank. Guess what? Sri Vivek also went to MEPCO. Then you can actually make the association saying, Frank and Sri Vivek could be potentially friends. Let me make that call and say that, because I'm looking at, so Minu, Frank, and Sri Vivek are basically nodes, and those edges that you're saying, Minu connecting to Frank, friend, Minu knows Vivek, that knows is another edge. And then of course there is another node called MEPCO, and then basically, and that could be the edge there is college, right? Frank's college, Frank node, college edge connected to MEPCO node, right? So that is really what we are representing here, right? We are taking we are basically breaking down this particular network so an SMT solver can understand this as a graph. So we are basically saying server A, server B are represented as nodes. And then we are basically connecting server A is actually connected to a network interface card A. Server B is connected to a network interface card B, and that basically becomes the edge for those nodes. Two nodes connected by an edge. What's the relationship? It basically transfers packets. The role of the NIC is to transfer packet to the server, and the role of the server is to send the packet, process it, send it back to the NIC, right? What is the relationship between a NIC and a subnet? Again, you can basically, you get the idea, right? So you can basically graph this network out into nodes and edges, right? And you exactly know what each of these nodes do, and you exactly know what is the relationship between these nodes, because they all have a 1:1 relationship with those edges, right? And that's how you really take a complex network and say, this is a secure network, and I'm going to break it down so the SMT solver understands this particular network for me, so I can actually make a decision without any human being telling me what is good or not. How does that do that, right? It's very simple, because when you look at this particular diagram, this is a complex diagram. What does a network do? Network do a bunch of things. What does a subnet do? Again, the subnet could be anything. It could do a number of things. But how do we actually define it to bring it to a particular scope? Actually gets pretty simple from here on out. We basically say, if there is a network and if a packet comes in and a route table defines that packet to go to a certain subnet, then we basically say the destination address should be within this /24 CIDR for me, right? That is the only rule we are going to say, this is the only rule. You're only going to allow a packet if it belongs in this particular CIDR group, right? Then it basically simplifies that, that relationship between that particular subnet and that particular network, right? And similarly, how do you know that within that subnet, how do you know which ENI or which NIC card to send it to? Again, that particular packet could have a destination address, and you're going to use that destination address. As long as that destination address matches, that's how I'm going to route my packet, right? And that's basically defined in your security group, right? So that's the other aspect of it, right? And of course, we can also look at the source of that, right? If the packet is coming in from the source address, should match that /8 CIDR. If it doesn't match that /8 CIDR, do not allow that packet, right? So that is another rule that you can again form. So you basically formed 3 different rules here. Subnet, the network should only route packets to this particular subnet. That's one rule. The second rule is the destination address should be this particular 1.4 IP. And of course, the source address has to be within this really, really huge CIDR, a /8 CIDR, right? Those are the rules you have formed. And now you know what the relationship is. And now you know what the rules of those relationships are. Now you have taken this and you have basically converted it into something that the SMT solver can actually understand, right? So with this, are you able to basically say that, I'm sorry, I kept going backwards. I should have gone forward. Here you go. Right. So this, with all of this established, you can basically ask a question to the SMT solver saying, can I SSH into instance A or server A from the internet? That's, you're asking a question sort of like in plain English, right? And that basically knows these are the rules that have to match for me to answer that particular question. And I know what those rules are to give you that answer, right? So that is what that SMT solver is going to go look at in that particular network and basically say, okay, the protocol has to be, for SSH has to be TCP. The source address, I'm going to look at the source address. Okay, that is well within the /8 I'm talking about. The destination address matches. Destination port is 22. I know SSH works on 22 because it's defined, right? Then it basically says, yes, you can basically SSH into that particular server, right? So that's how it really answers that question, right? Now, we call this particular service name is called, this particular technology that when we implemented, it's called TIROS. So that's why they are saying, questions that we can ask TIROS, right? But that's really the artificial intelligence, the AI mechanism that's implemented behind cloud security. It's also called provable security, right? So because you have mathematical proof to say that when we say something can happen or something cannot happen, we actually have mathematical proof by using these SMT solvers to say that I've taken the network, I've broken it down into zeros and ones, and I have basically giving it to the SMT solver for it to prove that something works or something doesn't work. So that's why they call it provable security, right? Again, these are just examples of, can an instance A connect to instance B? Basically, you get the idea, right? So in this case, it cannot because of the way the ACLs are defined here. The constraints are basically ACL A denies traffic to B, ACL B allows all traffic. So because ACL for A basically denies traffic to B, you can't really connect to this particular instance. Even though ACLs for B allow all traffic, it still gets stopped at the server A or instance A level, right? And that's how the automated reasoning group really works, right? I'm gonna basically stop here to see. Let me do a quick time check to see if there is questions, because I know we are 5 minutes over. But yeah, so this is basically the SMT solver, right? So we spoke about this breaking down and basically, applying that secret sauce. The secret sauce is basically people like you that have basically they know how this networks work, and they've basically broken down all the rules of the network, and they have converted in using SMT solver to reason, saying if something will work or will not work, right? So, for example, you actually launched a server, you launched 10 servers, and you did not have access, you did not provide access to SSH when you launched it, and then 3 months later, someone opened up port 22 to the internet all of a sudden, then this SMT solver is basically going to say that when it was launched, you basically told me that this is how secure looks like. Now, 10 of these boxes have port 22 open to the internet. Now I'm going to basically let you know, or I'm going to basically run a remediation rule if you have set it up that way. There are a bunch of AWS services. I didn't want to get into all the AWS services because it's still an academic talk. So I left that out. Plus, we didn't have time for within 60 minutes anyway, right? But that's really what it is. There is actually a really scientific paper that they published. You can actually go look it up, reachability analysis. This is not just for networks that they have implemented. They have implemented it for a number of other services also. There is data protection. There is identity and access management, policy analyzer. All of these things use the exact same thing that we just spoke about, using artificial intelligence, right? And there are lots and lots of academic paper. There is a university professor, Yuan Teen. She works for University of Virginia. She has published a phenomenal paper on AI, security using AI. She talks about brute force. She talks about a whole bunch of mechanisms that Microsoft, Facebook. She actually gave us a guest talk in our at Amazon. Phenomenal work that's being done. But again, this is a really recent field, right? So it's just starting to take off, right? But I'll stop there. I'll stop there because the next topic is basically starting to get into like AWS services that actually implement this particular technology, and it shows you how you can actually protect your network, actually protect your data, actually protect over privilege or underprivilege or the access control levels. But yeah, but we're almost 6-7 minutes over our time. Certainly appreciate you guys staying back and listening to me ramble for over an hour. If you guys have any questions, I'm happy to take them.
Sir, I have one question. Actually, yeah, in the AWS web services, any restriction will be there for application instances? For
Restrictions
example,
yeah.
actually, per application, how many user can access the particular application?
I mean, there are no restrictions like that. I mean, application, it's basically, absolutely no restrictions. Any number of users can pretty much, as long as your application is big enough, it's scaled enough, right? There is no restrictions at all. You can have tens of millions of users if you want to, right? Let's say you came up with this brilliant idea for an app, and then you go launch that app on AWS, and then that app really takes off and goes viral. Day one, you had only 100 users, and day 2 you had 1,000, and you start exponentially going viral, you can keep scaling it out. In fact, there are plenty of examples like that. Instagram was started on AWS, and when Instagram was bought out by Facebook, Instagram had 12 people, and Instagram was already a multi-billion-dollar business at the time, and Facebook bought them out, but they were running on AWS. There are so many. Airbnb was started, is still running on AWS. Netflix is still running on AWS. Amazon.com runs on AWS, right? We have millions and millions of users across the globe accessing Amazon.com, and that runs on AWS. No restrictions. I hope I answered your question, but yeah.
Yeah, yes, sir, yes, sir. Actually, one more question. Actually, you can create the virtual data center.
Exactly. Yeah, it is a virtual
Virtual,
data center. Yeah,
yeah.
yeah, it is a virtual data center.
What
And
kind of software you are using? For example, VMware or any other partnership
yeah,
you
so
can made it.
yeah. So we are actually on our almost we are in some instance classes we are actually on 6th generation of our instance classes. So when we started the business, the hypervisor that we used is a highly customized version of Zen hypervisor. That's what we started using. The 2nd generation that we are running right now, we are running both Zen, and we are also running a customized version of KVM hypervisor. All open source, but we take that open source, we basically because you have to understand, right? It's not
Yes,
just
sir.
about running a hypervisor,
Yes,
it's
yes.
about the scale.
It's made up of Python language. I know that in Zen and KVM.
Yeah, it's completely open
Yes.
source based, but
Yes.
that we were not running the open source version, just to be clear. It's a highly customized version of that open source frame, those hypervisors.
Okay. How to
Yeah.
handle the big data in Amazon? For example, in Cloudera, one of the big data environment will be there. How to handle the Amazon in big data
How
environment?
do you mean how to handle?
For
Like,
example, if you go for Cloudera, means a lot of databases will be there. CouchDB and Apache Spark and
So yeah, so
MySQL. Yeah.
we have a whole bunch of ecosystem that actually. Am I still sharing my screen? So we have our own set of, it's called EMR. So we have our own big data platform, if that's what you're asking for, how to handle. So we have something called EMR. We have Amazon Athena. We have Redshift. We have DynamoDB. We have Neptune, which is a graph database. We have QLDB, which is a time series database. We have, let me log in. I can show you the console. We probably have the highest number of databases because one size doesn't really fit all for databases. So we have a whole bunch of, if you're looking for, HDFS type environments, we have that Elasticache. Um, um, so I'm going to let it load here real quick. So just under machine learning, these are the number of services that we have just under machine learning, right? And where can I find? So this is just the database, relational database. DynamoDB is NoSQL, Elasticache, Neptune is Graph, QLDB, DocumentDB is a backwards compatible MongoDB. We have key spaces. We also have a time stream database, right? And that's just the database part. Here's the analytics part. Athena is basically Presto. If you've heard of Presto, Athena is basically Presto. Presto is basically used for unstructured, semi-structured, basically schema on read type environment, because you have a bunch of a blob of data. You don't have any structure. You don't have any schema. But you can actually go run SQL like queries on this particular unstructured or semi-structured data. That is what Athena. So it's basically based off of Presto. If you go look up Presto, Presto is the open source technology. But then again, it's a highly customized version of Presto that runs on top of the cloud. So again, every time you think about open source, you have to think scale, 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 scale. That is what is very different about the cloud, AWS cloud, right? Things that work for 1,000, things that work for 10,000, things that work for 100,000 may not work for 1 million, may not work for 10 million, may not work for a billion, right? For example, Netflix in the US alone accounts for 35% of the internet traffic in the US. And this is from 3 years ago. I don't know what their number is from last year or this year with the pandemic, but that's just one company. So imagine the scale at which the internet bandwidth that goes into these regions, the amount of data storage that you have to have, network congestion, jitter. You can think of all of these things, multiply that by 1 billion times or 1 trillion times. That's the scale at which the platform really operates. So that really is the challenge. Scale is the challenge, right? So EMR is the big data service that you're talking about. Of course, there is a whole bunch of other things. Kinesis, if you've heard of Kafka, Kinesis is very similar to Kafka. Of course, these are all managed services. Data pipeline, data exchange. Glue is basically, I'm drawing a blank here. Glue can be thought of as sort of like a ETL tool. If you can think of extract, transform, and load type tool, Glue is basically that ETL tool that connects multiple data sources. You receive a data source, you parse through that data, and then you pull something that you want, you look at that, and you take the interesting data, and then you transform that data, and then you go load it into a completely different source, right? So that's Glue. Lake formation is basically your data lakes, right? Petabyte scale data lake. And then you have messaging, message bus, and things like that, right? But this is just all of these services are just in analytics section. All of these things can work with all of these databases that you have here.
Yeah. Should it, any other question from participant side?
Yeah, I hope it was useful. I know,
Yes, sir.
like I said, it was a little bit of a philosophical talk, yeah, otherwise, since I'm not an academician like you guys are probably way more smarter than me. I would have to just go into this particular service and talk about the services, and it may not be very interesting to you.
Yes. Thank you, sir. Thank you for your wonderful session.
No worries,
And
my pleasure.
yeah, and I hope that all the participant getting insight of AWS in the security, what are the security applied in the AWS, and also getting a lot of algorithms. What are the algorithms used in the routing algorithms and different types of algorithms used in the AWS. I hope all the participants getting in some of the real-time knowledge in AWS. Once again, thank you, Mr. Minu Karthik, for your support in our STTP. Thank you, sir.
No worries. My pleasure. Thank you for having me. I appreciate that. Thank you.
Yeah.
Have a wonderful Saturday,
Yeah.
everyone.
Thank you, sir. Yeah. Yeah. Thank you.
Yep. Thanks. Bye.
Yeah. Thank you. Bye.